Idea behind the Mohr circle, because what we did last time, that we end up with the equation for the circle. Remember what happened at the end? So the discussion was that those three equations, which were equation 7, 5, 7, 6, 7, 7, when he turned it around and maneuvered between the square it and then add it together, we'd end up with a circle which has the following characteristic. First of all, the center of the circle is the sigma average. We decided on that one last time. Remember that? Yes, sigma average was sigma x plus sigma y divided by 2. Then we had an r. That's all you have to do. In order to draw the circle, which gives you all the information you want, you need two parameters. One is the center of the circle, where the circle is, and the other one is the radius, because the circle was symmetrical with respect to sigma. Remember that? Remember that. You cannot draw the circle up there or down there. It always is symmetrical with respect to the sigma, and I will explain that to you later on what happened there. So in other words, the circle, these are the format of the circle. The circle may end up like that, but it is symmetrical here. This is one principle. We said, oh, okay, let me explain that again one more time after we do that. Or the circle may end up half here, half there. Everybody understand that? Or the circle may end up here and here. This is all in compression. This is tension. This side is in tension. This side is in compression. This is all in tension mode. Is that understood? So there are all these three possibilities. Most of your problem are this way. Is that for the shaft and B? But nevertheless, all you need is, like here, you need the A. A is the, remember how the equation ended up. A was the sigma average, or was sigma x plus sigma y divided by 2, which shows the center of the circle. Doesn't matter. Center of the circle is here. Here I show you the C, the C, the C. Is that correct? Then, of course, you need the radius, and the radius was equal to, that's the, you want to rewrite it again, or it's already in your note. I'm sorry, sigma x minus sigma y, sigma x minus sigma y. Remember, this is plus, this is minus. They are not the same, so be careful then. This was sigma average is plus, this is minus, and tau xy. So of course, when the state of stress is given to you, sigma x, sigma y, and tau xy is there. Is that correct to you to start the problem with? So you do that, and you plot your circle. I don't know how much explanation I gave you at the end, but these are very important information from the circle. Now, remember, equation 6, 5, 6, 6, and 6, 7, I'm sorry, 7, 5, 7, 6, and 7, 7 was representing all the stresses in every direction. First of all, you have to realize what is the stresses all about. Please pay attention. If you put an object under the water, the hydrostatic pressure is coming from all directions, yes or no? This way, that way, but they are all equal. But if you go into a 3D body, like inside the wall or inside the soil or anything that is three-dimensional, the stress is coming from all directions too, but they are not equal. That's the whole thing. You have calculated your stresses in the x and y direction. Where this number coming from? This number coming from, as we said it last time, it comes from here. Again, this is symbolic. I'm putting everything positive. This could be plus or minus. This could be plus or minus. I'm putting it all plus. And this also could be plus or minus. So we always, in a plane stress scenario, we have a sigma x, sigma y, may or may not have, or we have a tau yx, which is equal to tau xy. The two tau are equal, remember? So that's the three unknowns, so that's equivalent to the three equation of equilibrium. If you go to the 3D, it becomes 6 of them, so that's become a little bit more difficult. So we are doing this form of analysis for your classes. Is that understood? Sigma x, sigma y will be given. You calculate that, you plot your circle. Let's say that your circle end up like that. That's for discussion purpose. So if my circle end up like that, both this is x and y is somewhere. We don't know yet where those are. So this is sigma. This is the tau. I believe I mentioned it last time that these 2 points become crucial points because those two are called principal stresses. Did I mention that last time or not? Briefly at the end, maybe you didn't write it, you want to rewrite it out. Those 2 points, which are the most important point in this circle, are principal stresses. Why? Because those one is the largest and one is the smallest sigma. Everybody understand what I'm talking about here? Please pay attention back there. So you don't. If I go here to this point, notice it has a sigma this much and tau that much. Because this is not x and y. Because people are not used to this, they think this is x and y. This has nothing to do with the x and y coordinate axis. This is sigma versus tau. Therefore, look at this plate, this direction. This direction has a sigma and a tau. So if sigma is 10 and tau is, let's say, 5, I have to go here on the sigma, I have to go 10, on the tau, I have to go 5, and then that's become a point. Is that correct or not? So each point here, which is on this circle, because those 3 equations end up like a circle, yes or no? On the circumference of this circle, this point has this much sigma and this much tau. Is that correct or not? When you look now at the circle, you are not interested in that one as much. You are interested in this one because this is the highest value of sigma. Is that understood? Yes, which we are going to call it principal stresses. In the handout, I call that one A or B, but this is the result after you plot it, which you need only 2 data, 1 and 2. That's it. These 2 gives you the circle. Yes. Now this is the analysis of the circle that everybody should remember. You call sigma A. You can call it in this problem sigma max because this is the highest value. And how do we get it? Look what happened. This is sigma average, yes or no? Because the center of the circle was at sigma average plus what? Plus R, yes or no? So sigma principal 1 or sigma max, or you can call it sigma principal 1 for future. Here in this book, we only call it A or max, becomes sigma average plus R. Is that correct or not? This is O, C, and this is very important point because that has the large, any other point on this circle coming from the 3 equations are smaller. So this is the one I was looking for. So you are always looking for principal stresses at the end of design, and this should be less than sigma allowable. Is that understood? Because that is there. And it is not in the x and y direction. It could be here or could be there. We are going to talk about it in a minute. Then we get sigma b. What's sigma b equal to? Sigma b is, we do the same thing, sigma average minus r in order to be routine. In this case, we call it sigma minimum or sigma principal 2. And then there is sigma average minus r. Now, what is important here is when we go to the point A and B, what's the value of the shear there? The value of the shear is 0. That's very important. People disregard that. If you disregard that, that tau equal to 0. So if I give you a state of stress that has only this and that, nothing there, tau equal to 0, you already have the principal stress. You don't have to draw the Mohr circle. Everybody understand what I'm talking about. We go through an example. I'm going to explain that again. So nevertheless, the coordinate of this point is sigma max, and tau is 0. You see, you have to change your mind from x, y to sigma and tau. Everybody else. Sigma is sigma max, but tau is 0. Here, coordinate of B is sigma minimum, or the second principal, and 0 as well. Is that correct or not? There are 2 more points here which are also as significant. What are those 2 points on the top and bottom? Why? Because those shows the maximum shear. That's right, the maximum shear stress. So therefore, if I'm looking in my handout, I call this one D, I believe, and this one E. But here you have a sigma as well. So sigma average for this point, if I want to calculate the coordinate, the sigma is sigma average. Everybody understand that. But it is plus R because it's going up. And this one is sigma average minus R. Is that correct? The coordinate of that. Because these 2, sigma principal, 0, 0 shear, 0 shear. This is the highest shear, this is the highest shear, plus R minus R. But there is also a sigma equal to sigma average. Is that correct or not? So these 2 become of interest to you. And then, okay, we find the value of that. The next one is how do we, where they are. Remember, X and Y are not principal stresses. X and Y usually, as you saw it in the example I did for the drill, this is what happened. I give in the drill, I give you the state of stress. Then I went 22.5 degrees, all the stresses changed, yes or no? And some of them got larger, some of them get, I believe that sigma become larger, and the tau become smaller for that particular problem. Then we decided, okay, as I go along this way 22.5 degrees, since it is changing, maybe if I go 32.5 degrees, I get to the highest value. So the next question you want to answer here is, where are they? So the question you want to write in your note is the following. These questions are going to be asked typically in your final or in the quizzes or in this chapter. Find stresses at theta equal to, let's say, plus 15 degree or theta equal to minus 30 degree. I'm sure if you look at your final, you see, or your homework, that's what. How do you answer that question? I'm going to go through all the questions one by one related to this circle. Okay? I gave you only one method. The second method is finding that from the circle. I don't have time to do that. I will do that for ME 219. But I already give you a solution. What did I tell you? Remember from last lecture? How you find the stresses? If I give you this state of stress, this is X and Y. How do you find the stresses along X prime and Y prime? The whole story started from there. So you should have the answer. But you are not putting 2 and 2 together. What is those? Where should I look for it? Equation? Come on, guys. Open your handout. That's what the whole thing started from there. Equation 7.5, 7.6, and 7.7 are the stresses in the other direction. Yes or no? Correct?
Yes.
Come on. See, you already have it underlined in yellow. That means you should pay attention to that. See, if you don't get the idea there, none of this should make any sense to you. Is that understood? That in chapter 2, I don't have time to, that's luxury. I only have 40 minutes or 1 hour to finish the whole thing, and I have to keep repeating back because you are not responding. So we did this for sigma. We find the stresses in the X prime and Y prime. The whole lecture last time started by going through that and then rotating it theta degree to come up with the equation. I give you 2 sets of equations. Go to previous page. See, that was the whole idea. Go to page 5. Where is your handout, my friend? You need all of this. Otherwise, you cannot look at me or at the wall or the ceiling and then get all the information there. You have to understand what is the question. Many of you guys have a problem because you are always looking for a recipe without paying attention to the question and what question is and what are we doing. If you don't know what we are doing, forget about the solution. Even if you learn the recipe between now and next week, some of you do it that way, then the next morning when you get up, you go to another exam, you are going to forget all about it, yes or no? That's not the way to learn this material. You want to understand it. Is that understood there? The understanding is this. I'm asking question. None of you responding there. I changed this from X, Y to X prime and Y prime. I end up with these 3 equations at the bottom of page 6. You see that? First. Correct? But then Mr. Mohrs changed that. Remember, I said he changed the sine theta to cosine 2 theta. Remember, sine. And then end up to equation. Look at next page. And the whole start from. Anytime you want to calculate stresses in any other direction, you have to use this. Correct? Then we decided, this was all this past Tuesday, we explained that. So I don't have luxury time to explain that again. So we said, okay, if it is changing, so if I want to find the highest value, I have to plot this equation between 0 degree to 108 because X again become X. Is that understood? That not 360, 180. Instead of doing that, which I have to keep repeating 50 times because I have to go between 1 degree, 2 degree, 3 degree, and then I have to go between 22.5 degree, 22 to 23 degree because I want the exact. Is that maybe the answer is 22.57 degree. Everybody understands, so you have to do it 1,000 times. Instead of that, what are we doing? We turn these 3 equations into a circle, get all the answer from the circle. Is that understood? That's the question we want to answer that. So if I ask you find the stresses at theta this, what do you use? The answer would be, use equation, write it down in your note. Use equation 7, 5, 7, 6, and which I did it for the drill as well. Remember, I did for the drill, and I end up with a new set of equation. Did everybody understand? Then set of answer. Yes? Correct? Okay, good. So question number 2. Find principal stresses, which also could include find maximum shear stress. Now, both of them has been answered here. If I ask you that question or that question, what should you do? You should plot your circle. These are principal stresses, yes or no? Correct? What is maximum shear? Maximum shear is the radius. So I'm putting the answer. This you put, use, this is how your notes should read for yourself in order for future you have no problem with any question. Then this is what you are not doing, guys. You are not relating all the subject to each other. So that's why we are, if I want to do that, going back again, use equation 7, 5, 7, 6, 7, 7. This is one method. There is another one to be able to use it from the Mohr circle, which I don't have time, unfortunately, to do that. So I leave it at that. Leave that the rest of it for ME219. Everybody understand, because we are going to use the ME219 a lot more circle, more than here. Here we're going very brief. For this one, draw the Mohr circle, and then from Mohr circle, you just get sigma principal 1 and sigma principal 2, or you can call it sigma A or sigma B. Is that understood? Yes? Which I'll show you there, correct? This one is also very important. That is tau max is coming equal to R. Is that I just put the magnitude because the sign, I will explain about the sign of it after we plot that, correct? All you need then, this, and this calculation, which is very simple operation, yes? Now, what is left there? What's left there we really want to know. Where is this principle happening? Is it happening at 10 degree or 22 degree or 50 degree? We don't know that, yes? We want to find that. That, I believe I didn't give it to you. Now, to calculate that, remember that. Where is the principal stress? At principal stress, the shear stress is equal to 0. Look at the equation of shear stress. The equation of shear stress is equation 7,6. Is that correct or not? Do you see the 7,6 there in your handout? Yes? Put that equal to 0, because tau has to be 0, and then you find the theta for the principal, yes? I don't have time to do it, so all I'm saying that if you question number 3, directions of principal stresses and maximum shear. There is 2 of them, because they are not happening in the same direction. Because maybe principal stress is happening like that, the shear stress are somewhere else. They are not at the same location. Is that understood? There is a relationship between the two. Well, I'm going to show you. That will do the following. In order to get that number or that equation for this, since the tau is equal to 0, I put equations 6, 7, 6 equal to 0. Look at it. It becomes a tangent. Everybody see that? If that equation becomes equal to 0, so you get sine of 2, where is that? You get that, here is the, you get sine of 2 theta divided by cosine of 2 theta. Do you see that? Yes? So this equation, you end up with this equation. Tangent of 2 theta, theta p, set tau equal to 0, tau xy equal to 0, or x prime y prime, or equation 7, 6 or 7, 7. Which one is it? Is it 7, 6 or 7, 7? 7, 6. That's right. That's what I thought. Yeah. 7, 6. So as you see that gives you equal to tau xy divided by sigma x minus sigma y divided. Notice in the book they put the 2 here, but I'm going to use the same system as R, because R has this quantity and that quantity, so I change it a little bit. But that's the 2 theta. That's where the principal stresses are going to be. Is that correct or not? And similarly, the proof is in your handout. You can read it. We can find the direction of maximum shear, because this is somewhere else from here, different from each other. And for tangent of 2 theta s, s means shear, p means principal. Remember, these are the principal. These two are maximum shear. Is that correct or not? They are in 2 different directions. So that's the direction of you calculate from this equation, theta p. From this equation, you calculate theta s, which for our drill was not 22.5 degrees. Should be a little bit larger than 20.5 degrees or smaller, each one of them. Is that correct or not? There is a relationship between the two. We'll see that in a minute. So that one is actually minus and then reverse of that one. Sigma x minus sigma y divided by 2 divided by tau xy. Can you tell me what relationship is between theta p and theta s? Can you see that? Yes, in reverse, inverse with the sign. What does it mean mathematically? 2 theta p plus 2 theta s must be equal to 90 degrees. Is that understood? That is a relationship. Look, if tangent of the angle is x and tangent of the other angle is minus 1 over x, the 2 angles are together are 90 degrees. This is math. That's calculus. Everybody understands. So the result is this, which is very important. So if you calculate one, do not calculate the other one. It's a waste of time. Just use the 90 degrees. So what I'm saying that 2 theta p plus 2 theta s, because of this relationship, must be always equal to 90 degrees, or theta p plus theta s must be equal to 45. Whether you use that or use the formula, I don't care. All the formula will be given to you. Either way is correct. Is that understood? But if you want to have more knowledge, that's what. So we have answered all the questions. Is that correct? So let's now do the example. Okay? To do the example, look how simple this becomes. I'm going to make example very simple because it is the one that I did for the drill is in the handout. I hope I have some time to explain that to you, but nevertheless, let's do another example which is simpler than that one. Now I'm going through the whole operation, answer all those questions with a simple problem like that. Now, first of all, let me give you the state of stress. Now, where is this state of stress coming from, guys? Of course, we know that. We are spending 10 weeks on that one, yes or no, to calculate sigma x and sigma y and tau xy. I put that on the board for you last time. You may or may not have sigma x in all your problems. You may or may not have sigma y. Again, sigma x and sigma y are coming either from chapter 1, which is P over A, is yes or no, or chapter 4, which is bending, MC over I, because those are the sigmas. Is that understood? I said that before. It is in your handout. You should remember that one. The sigma, any sigma, that's why I don't put X or Y here. Any sigma is either plus minus n. I put it n over A for you, that you do not make a mistake there with the P. Is that correct or normal, which should be at the centroid of the cross section, or plus minus MC over I, which is the bending action, correct? You have this pipe, you pull it, here is a tension, yes or no? You bend it, here is a compression. You bend it this way, here is also a tension, so it changes. The moment you get plus or minus, depend where you are, on top, on the bottom, on the side, etc. You may have even on the side, if you bend it like that, on the side there is no effect because it is on the neutral axis. Everybody, we went through that. But what I'm saying that when you see this, this is coming from state of stress that we have gone through chapter 1 and the tau generally comes again. What tau we have to see which plane we are. We could be x and y or y and z or z x, etc. But tau in general we call this sigma x. In general we call that tau x. Well, it's coming from plus minus tc over j, which is chapter 3. Remember we have gone through that 10 weeks. We did this. And we cut it here. The stress either goes that way, depends which way you are. The torque is. The torque goes this way, the stress goes up. Everybody under. Torque goes this way, the stress is going down. That's TC over J, yes or no? Then we had chapter 6, which you just wanted to give me the homework. I said I'm not going to collect that. That is VQ over. So in this section, you may have a force going down or a force going up. So it's nothing on top, nothing on the bottom, but here and here. Is that correct? You get the maximum on the neutral axis, which is VQ over IT. The Q become Q of half circle. Is that understood? That? So therefore, all of them are coming there. Now, of course, the tau xy will be there, so I'm now going to change that to the number now. So let's say that this one is 11 KSI. And this is our example, just the Mohr Circle example. As I said, I choose the simple one. I have to find out where is my numbers. I'll put it here somewhere. Okay. Lost it. Nope, here. Yeah, here it is. 11 KSI, and here is 5 KSI. And the shear stress going this way. The result of all of that is 4 KSI. Now, it could be 1 or 2, I don't care. This is the state of stress. Usually, chapter 7 starts with the state of stress, assuming you have gone through chapter 1 to 6. Is that understood? Yes? Okay. Now, first thing I will ask you always to do in order not to make a mistake, people make mistake with the sign. This is tension. This is, if it is compression, you should put a negative here. People forget about that, then all the equation changes there. So here, our sigma x is plus 11, so please write it down. Sigma y is plus 5. If they were compressive, you have to assign negative to that. And tau xy is what? Plus or minus? Negative. That has to be specific here. You cannot this. You see, in previous chapter, I said give me the magnitude, but I said remember sign for chapter 7, because if you put a negative in this problem, because everything is changes. Everybody see what I'm talking about. So you have to be correct in the sign of every one of them. Is that understood? Yeah? Now we want to draw the circle. We want to answer. First of all, this one I'm not going to do it because I did it for the drill. Remember that? I put the equation in the drill. We got that. That was last Tuesday. Is that correct? So now the subject is this 3, correct? So look how simple it is. What should I do? Find the sigma average and find the R. As simple as that. And then plot your circle. You need a little graph there in front of you. I hope in the final I would give you the graph paper, usually with the final, but you should need something to draw a nice circle, however you want to do it. Don't do like the one I do ugly here. So therefore, here we go. So you need the sigma average. Absolutely. What's your sigma average? The sigma average, you look at this new number, is 11 plus 5 divided by 2, so it is 8 KSI. So the center of the circle is at 8, whatever scale you are choosing, 8 KSI. And then you need, of course, the R. Is that correct or not? The R will be given. All the formula, you should not remember any of this. All the formula will be in the formula sheet. It already is with your final. The same formula sheet. Don't bring that one. I'll give you a new one in the final. Is that understood? Yes? So it is tau, it is sigma x minus sigma y. So it is 11. Notice this is plus, this is minus. I have to mention that because I have seen many mistakes in the final. They put here plus, they put here plus 2. That's wrong. Is that understood? Yes? And then plus tau xy, which is the 4, so 4 squared. So you just do that. This becomes 6 divided by 2. 3 squared plus 4 squared become 5. So the radius of the circle is 5. That's it. That's the end of the story. Yes?
Even though tau is negative, you put it in this column? Oh, it's...
That is the mistake you guys make.
It's always the opposite.
That's how it is. Absolutely. Very good question you asked. I was going to mention that, but anyhow, you just add up me a little bit. Minus 4 squared. It is not minus tau squared. It is plus tau squared, but the value of tau is negative. Negative squared become positive. Unfortunately, I have seen many mistakes there. Good question. Is that understood? Yes? So therefore, the same thing here. This is sigma x plus sigma y. This is sigma x minus. And they are negative. You have to put negative here. So you have to be very careful. This is it. That's good. Now, we want to draw the circle. This is what we do. Here, horizontal axis is no longer x and y. This is the sigma axis, and this is the tau. So you go here, scale it. So you go 1, 2, 3, 4, 5, 6, 7, 8. So that's the center of the circle. Yes, with the scale, hopefully. What's the radius? The radius is, you already draw it. Yes, the radius is 5. So therefore, you have to go 5 more. 1, 2, 3, 4, 5, or 5 back. 1, 2, 3, 4, 5. So 1 point is here. These are already your 2 principal stresses. Is that correct or not? Yep. So you draw, this is the center of the circle, which is the sigma average. Sigma average, that's what I said earlier. Then you draw your circle. So I usually have to draw my circle first before I do that. Everybody understand that? So this is 8 plus 5, so this is 13. That's 8 minus 5, so that is 3. You already have your two principal stresses answered, sigma principal 1 and sigma principal. Well, how we do it is, let's do that. Let's draw the circle first. Because here I cannot draw that, fit it at all this point. So my best way is to draw the circle and show you the number there. So hopefully this is a better circle, not good. As I said, my circle always are bad. So after all this year, anyhow. So that's a little bit better. So here it is. This is sigma. This is tau. This is 3, and that is 13, and that one was 8. Is that understood? Yes? 8 plus 5, because that's the number I need. So sigma principal 1 equal to sigma A equal to sigma max. How you call one of them, not all three. I'm just giving you different option. Is that understood? Which is this point, A. So that is sigma average plus R from the graph. 8 plus 5, 13 KSI. Notice 13 is much larger than 11. So if this is less than sigma allowable, then your structure is safe. So you calculate X and Y. Principal stress is the one you want to check it versus the factor of safety and all of that, because these are larger, yes or no? And the shear, you don't go by this. In other words, if you check this and this versus your factor of safety, you are not correct yet. You have to go to the Mohr Circle. So you appreciate that every design has to go through the Mohr Circle before, because the stresses are not maximum on the vertical. You never find any surface like that, which is a plate, cracks vertically, and it may, but that's the different reason. Usually the crack is along the theta P and theta S. Everybody see what I'm talking, where the shear is maximum and where the normal stress is maximum. Everybody getting the idea there? So these are the points you want to put in your design. So it happened there, every design. So next class 219, which is more design, we do the shaft design, we do beam design, and all of the subjects end up with a Mohr Circle. Even in civil engineering, you have a dam or you have a foundation. When the soil fails, the soil goes through the Mohr Circle. The failure is all due to these principal stresses. I want you to, not the one you are calculating. We spent 10 weeks calculating stresses in the X and Y direction. Look how important this chapter is. This chapter gives you the final analysis. Is that correct or not? See the significance of these two. And then, of course, that's what's the maximum? Notice, again, one more important. This is 13 and 0. And this is 3 and 0. Is that correct or not? Because shear stress is 0 there. So actually, and then sigma principal 2 or sigma B or sigma minimum so is equal to 8 minus 5 or 3 KSI, and tau equal to 0. We put all of them here to show the point A and B. Is that correct or not? Yes? But if the second question was, what is the highest value of maximum shear? Of course, the maximum shear will be at point, I'm sorry, I usually show this as center. I call it in my handout D and E. But at D and E, now look what happened. D and E show two things. First of all, you have this much sigma here, so don't forget about that. People forget about that. The sigma here is not 0. The sigma here is 8. So the coordinate of that point is 8 and plus 5. And here is 8 and minus 5. I'm going to explain that plus and minus later on. One is plus, one is minus. But that's why I put here, I said use the absolute value, because one is plus, one is minus doesn't make sense. Is that correct? There is a theory behind that. I will mention that later on. So that the value of that is 5. Is that correct in magnet? And that's what you need for the design anyway. So therefore, we want to calculate tau max. You answer your answer will be R, and in this case will be 5 KSI. Notice how simply you answer all those questions, yes or no? This set of questions. Now you look in the final, you see this, you see it, it should mean something to you. Is that correct or not? So I'm relating everything together, and that is the way you should study every chapter. people go through chapter by chapter not realizing what is the goal of the whole chapter. That the goal should be defined first before you go into analysis. Yes or no? Especially when I give you all the formula. Yes? All right. So what else is left there to do? Find the direction. Where are they? They are certainly not along the x and y, because along the x and y are this number, 11 and 4. Everybody see that? This is perpendicular to the x-axis. This is surface perpendicular to the y-axis. These numbers, this 13 and 3 and 5 happening somewhere else. Where are they? I gave you the equation. It's sitting right there. Is that correct? I have to calculate tangent of 2 theta p, so you don't have to rewrite it. So you write your note right now, write it tangent of 2 theta p. I put it in front of this, that you know what I'm doing there. Equal to what? Equal to tau xy. What's the tau xy value? Negative, not 5. From x and y. You don't go with the principal. We are calculating that. Oh, it is from x and y. You see, it is tau x and y. It's not x prime, y prime. So you need 4, and it is negative 4. Yes or no? Don't forget. You put plus 4, you are in trouble. That is, look at it. It's sitting there. First row, first column. Everybody see that? That is, tau is minus 4, correct? From your state of stress. Minus 4 divided by sigma x. We already calculated that. Sigma x minus sigma y divided by 2 was 3. Is that correct or not? Yes? 11 minus 5 divided by 3 becomes 6 divided by 2 or 3. Get your calculator and give me that number. I have it here as if it is your quiz or your homework. So immediately you calculate that angle, and that angle end up to be minus 53 point, I don't know, something like that. Minus 53.3 degree, yeah, 13 degree. That means I should not go counterclockwise. I should go clockwise. Everybody understand? However, this is 2 theta p. Do not make mistake. We need theta p. What's the theta p? Is half of that. So minus 26.5 and has, let's see, 6 approximately. Is that correct or not? Yes? Okay. What we are talking now about is the following. I know my principal stresses are 13 and 3. Yes or no? And I know the direction of it is at minus. So x and y has to travel. Please, I explained it again last time. This is x and this is y. If you go that way, that's plus. If you go clockwise, that is negative. Yes or no? So what you should do next is the following. So therefore, I'm going to erase because this was all the question. I'm on the question 3 now. You see, I already answered all this one, the last one. And this is exactly what is happening in all your questions. So therefore, we go there. Now, if I ask you, give me the number, that's the number. If I ask you to plot it, this is the plot. Everybody on the plot of a state of stress for the principal. Yes or no? Now, here it is. You draw your x there, and you draw your y there. Now, what angle do I need to go down? I have to go clockwise equal to 26.6 degree to get to my principal stresses. So here it is. So here it is like that. So you put the other one, of course, perpendicular to that. So you have shifted your direction from x and y to x prime and y prime. And this one is 26.6. And I'm going this way because that way is negative. Is that correct? Clockwise is negative. Yes? OK. What should I put there? I should put one of the principal stresses here, one of the principal stresses there. Yes or no? So this one, for time being, let's put it this way, then I explain it later. This becomes 13 KSI, and this becomes 3 KSI. Should I put any shear there? No. 13 and 0, 3 and 0. Everybody understand that? Yes or no? Correct? So that means this is principal stresses now. So I'm going to use a color coding system here for you to understand what I'm doing that. Let's say that we started with the black. The black is the originally state of stress. These two, I'm going to make it blue. Is that correct or not? Yes? Look. This is the blue surfaces. Everybody see that? And that one, and 13, 0, 3, and 0. Everybody see what I get? Yes? So now, look what happened. Is there any shear there? No. There is a crack here, appear here. That crack going to be immediately open up, not because of 11 KSI, because of the 13 KSI. So in every object, like for example, you are sitting in the airplane, all the shuttle, everything, there are thousands of, depends on how big the airplane is, of course. And there are thousands of gauges there. You know what the gauges are. We talk about it. Gauges are strain gauges, yes? They measure the strain. So if something happened here, so let's say the heated in this area part of the airplane, there is by mistake, there is some heated area, the stresses keep increasing. So the strain gauge shows you the effect. If there is slightly a crack here, the strength of the material become less, the stresses become larger. As the result, the strain become larger. Remember the strain epsilon and gamma, is that understood? Yes, what we are talking about? Then the red light comes in the cockpit, so the captain has to stop the airplane. Doesn't know what the stress is, but remember that if a crack starts here, this is going to open up because it is in tension mode. A crack appear this way is less critical because it is 3 KSI. Everybody understands it's less dangerous. So maybe you can fly another half an hour. No. Is that understood what I'm saying? That yes? However, it's in compression, probably is not as critical. Everybody understands. So this could be tension or compression. However, we are now exactly knowing where is happening here. So in other words, this principal stresses are at +2, and everybody see that those are the direction of principal stresses. And this is the plot of it. Did I ask the plot? So if they ask you to plot it, this is the plot. Is that correct or not? Now let's go to the maximum shear. The maximum shear, we do the same format. We calculate this, or I use the other equation that I show you. The other equation that I show you was 2 theta p plus 2 theta s was equal to what? 90 degree. So since the 2 theta s is minus, so therefore actually you have to don't calculate it that way. 2 theta s become 90 minus, usually we do that, minus 53.13 degrees. So we don't go by the sign like that. Well, I'll explain that again. So that one become equal to 36.89 degree, or theta s become equal to 18.4 degree. But this time is plus, therefore I have to go that way. So we go either plus or minus, and there is an explanation for it. Hopefully I will have enough time to explain that to you in a minute. However, you calculate that one, and then also you plot it. But plotting it is a little bit difficult to do. But before I do that, I want to show you, yes?
Since 53.13 is negative, shouldn't it be positive on the right side?
Let me explain that to you, okay? So before I do that, let me explain something else. As I said, because also plotting it is a little bit difficult, so I have to explain what happened here. So let's leave it at that for time being until I tell you what happened there. What happened here, that there is another method to explain all of that, and that's the graphical method. Is that understood? In graphical method, we get all the information simply without using any of this equation. I'm going to mention here, but since I don't have time to practice this you with often, so for the final, I leave you open to use your equation the way I did it. But I'm going to explain it. Some of you may be good at it and they want to use that method. It's perfectly all right. But if you don't do it, because we don't have enough time to cover this in detail, so I'm going to not to ask that question. Is that although half of your homework was with graphical, so if you cannot do it, don't worry about it. That question will not come in the final. Is that understood? But to answer all your questions, plus minus, you need to know that. Is that correct? And this is the following. So let's say go by the graphical. The same question that I did here, let's do it by graphical. In order to do the graphical, notice these two are principal stresses, and I did not finish my discussion then because I went, and let's say these two are maximum shear direction. Is that, where is x and y? X and y must be somewhere there. Is that correct? Because this circle represents all the stresses, including x and y. But x and y is not there. This is not x, guy. Forget about that. This is not x. This is not y. This is principal. I show you there. This is the principal, which is at 22.6 degree there. In order to get exactly all the information, you need this. At least you should do it for your homework, all the homework. You need to show this on the circle. Yes? Okay, to do that, we do the following. Okay, please rewrite that. This is using the graphical method, but I am not going to ask you to do it all the way, but at least do the x and y on your circle. Everybody understand what I'm saying? That way it will help you to answer all your questions. Now, here we go. This is your sigma. This is your tau. Now, what is the stress on this direction? This is the x direction. Notice you have a sigma and you have a tau. There should give you a point there. Yes or no? Where is that point? 11. Yes or no? Where is 11? This is 13. 11 is here. Is that correct or not? I'm going to go back to redo it. That 11 here. Then I have a shear of how much? The shear of -4. Is that correct? So if I go down here, I should get to here. That's on the set. This is your x. Is that correct or not? However, there is a minor change here. That's why it is so difficult to explain that. So let's go here and do exactly the same thing as the following. So all you have to do plus x and y. X and y are on the circle, yes or no? If I get that point, I can start from there. Let's understand what we have here. We have 11 and -4. Here we have what? 5 and -4, correct? Okay, so let's do that. So here go 5, 10, 11. Then I go, don't do it yet. So that seems to be direction of the x, yes or no? And this one is 5. This is 11. And then -4. Is that correct? That should be your y. Yeah, correct? Yes? Look what happened now. What happened there that was a problem with Mr. Mohr, and should be a problem for us too, is the following. Look, guys, like this. This looks like this. Is that correct or not? I had it for the other class. Is this correct or not? Notice this is negative, correct? This is x. This is y. It's negative. But if you have a state of stress sitting here, somebody may look at it this way, somebody may look at it that way, yes or no? So x become y, y become x. As far as the stress is concerned, the normal stress concerned, this is always tension and this is tension no matter where you look at it. But if I change that, everybody see this is negative. If I change x to y and y to x, look what happened. Is the tau negative or positive? Suddenly, did you see what happened there? So if I look at it this way at my state of stress and I look at it this way, I have to give a different sign. That's exactly what Mr. Mohr has to do. So he gave these two, not both minus sign. He gave one plus, one minus, because he could not get this down. In other words, in effect, this is the just word. This didn't happen, but I say it this way. By doing it this way, x was here, y is here, so both point was here. Everybody understand that? He didn't recognize that. He wanted to see that sign change, so he put one of them up, one of them down, giving one plus sign, one minus sign. Therefore, this end up like that. Everybody's doing like that. By doing that, so therefore half circle, the two half circle, which I call it taco shell, was like that, suddenly become burrito bread. Everybody understand what I'm saying that? So therefore, in effect, the reason was what I just told you earlier. So he put here if you look on the book, you see that. There is a little arrow there. Everybody see that. Any shear stress going this way, he puts it up. Any shear goes stress that way, he puts it on the bottom in order that 180 degree become 360 degree. Remember the joke I said that really that was not the case, but what I'm saying that's why he has to go and change all his equation from theta to theta. Remember that? So all the angle here become twice as much. So that's another thing. So therefore, let's go one by one, not mix all of them together. So let's plot ours. Now in plotting ours, so I have to go 11. Then is it clockwise or counterclockwise? Look at the shear. Is it this way or is it this way? Which way is it? Look at your shear there, original shear. Is it going this down here or is it going down there? Down there, that way. Yes, so I'm going to go up, not down. So this becomes your x. Is that understood? Yes, so change the sign a little bit. So therefore, but the y, when you plot the y is 5 and plus 4, yes or no? Because it goes this way, correct? Or put it this way, guys. This way and that way. Is that understood? Yes or no? Correct or not? Yeah? Yes? So for the other one, it should go down. Let's do it again one more time so to be correct. So here we go. Guys, 11. This, I'm plotting the x. I go 11. Then instead of -4, I'm going to go upward or +4. So that becomes x. And here I go 5 and 4. And these two are on the circle. I connect. All I need is this little triangle. That little triangle gives me all the information I need. There is no equation needed. What is this length, guys? Look at it here. What's this length? 6. What's half of that? What is this? What's the r? 3 squared plus 4 squared equal to? All these numbers are in your equation without you realizing. So you really don't need the equation. You need that little circle. Yes or no? And not even that. Look what happened here. Theta p is going this way. Is that correct or not? Where is your x? Your x is here. In order to go to the principal, which direction should I go? Look at it. It's showing it. This is your 2 theta p, 4 over 3. Is that correct? 4 over 3. But most importantly, it's showing it should go going this way. Now answer your question. You ask you why I changed the sign. Look at what happened there. If I want to go from here to the maximum shear, which direction should I go? Should I go clockwise or should I go counterclockwise? Counterclockwise, equal to the balance of 90 degrees. Did you see that? Look, guys, one more time. This is, okay. Here we go to this one. If I plot it here, this is your x, this is your y. Is that correct or not? Yes? Do you see what I'm talking about? This is the black, this is the blue, this is the purple. Is that correct? The black is your original state of stress. Now, all you need is this triangle. You don't need any equation. Actually, in ME 219, if you come to, I would not give you any equation. All you have to do, plot it like that. Is that understood? Now, look what this is. This distance, this is 11, this is 5, this is 6, this is 3, this is 4, this is 5. It just takes a few seconds to do it rather than all those formulas. Yes? Okay? However, the answer you asked me, this is 2 theta p, this is 2 theta s, because this is your x and y, correct? This is the black one. If I want to go to the blue, look how am I traveling? How am I changing this? I'm going clockwise, which is negative. Did you see that? But if I want to reach to the D, for example, which is, I can reach it that way too. But if I go this way, which way do I go? I'm going counterclockwise, and I'm going that way. Is that correct? So that is the answer to your question. You can go the shortest distance, or the other way is correct too, but that's the other one. Is that correct? So there is 2 answers to that. Did you see that? Okay, so if you plot your x and y, so in other words, theta s, here, theta p is 26, and theta s is equal to 13 point, how much that become? 18.4, and this is like that. Look at the graph there. If this is 53 degrees, this is 36, and you have to take half of it. Is that understood? So all of that is there, so we are done, we are finished, and everything. Now, let's plot the last one. The last one is now plotting the purple. Yes, again, plotting, I may not ask you in the final because you have not practiced this one, but you should answer all this question by the formula. Everybody understand that. Plotting, I'm doing it for you in order for you guys not to miss anything, but since I do not have time to practice that more with you guys, I said I will not ask that question in the final. No plotting. However, since some of you already know that or advanced in this one, I'm going to plot now the shear as well. Is that correct or not? Now, this was the blue one, correct? That's the black one. One more time. This is the black, this is the blue, this is the purple. This is the original state of stress, correct? This was the principal, and this one. The principal always is this two. The x keep changing. X could be here, there, because I can go there. The circle could be here. Depends whether the values are plus or minus. If you look at the handout, there is a circle for the drill as well, which I'm going to show you in a minute. I did not show that for the other class, but I'll show you here. So because I ran out of time, but here we go. So this is now the plot for the maximum shear. Now everything is on the circle there. Don't forget that. This is 2 theta p, and this is 2 theta s. Is that correct or not? Yep. The sum are 90 degree here. Of course, everything here is double. Remember, this was, oh, I did not show that. This originally was like, or I did show you. This originally was like that. It opens up. Is that correct or not? Therefore, look, here is interesting part. X and Y here is how many degree? Here is 90 degree. X and Y here is how many degree? That was because of that change in the sign. Is that everything here seems to be double. That's why it's a little bit confusing. Every angle, write it down in your note. Every angle on the circle is twice as much and on the standard X and Y coordinate. Correct? Yes? Do you get this one? Or did I confuse you more? Here, look, guy, is this X and Y? Yes? Look what happened here. X and Y is like that. Is that correct? Because every angle is, that's why look at the equation, the difference between the equation on page 5 and equation page 6. He changed all his equation from 1 theta to 2 theta because he was going to use this sign convention. Is that, which is a little bit different from that. Nevertheless, now here we go again. X and Y. Which direction should I go? I should go, according to the picture there, I should go, if this was, remember, you don't need to use formula. Here you calculate 2 theta p equal to tangent minus 1 of 4 over 3. This is 4, this is 3. So 4 over 3. So it becomes in magnitude 53.13 degree. In magnitude, 13 degree, sorry. And then the picture shows you that you have to go clockwise. For this one, you have to go counterclockwise, yes or no? So therefore, effectively, this is negative, which you got it from formula, and the other one is positive. Now we're going that way, the same way. So therefore, here we go. This time we have to move upward. How many degree? We have to 18.4, correct? Very good. And so that becomes your direction of your maximum shear. Then you put your element there, perpendicular to that. Hopefully it is perpendicular, something like that. It's not exactly, no, I'm sorry, it's not perpendicular. I should have better job for that one. So let's do it like this. So this was X and Y. This is now your X prime and your Y prime, which this time should be the maroon one. Is that correct or not? Yes. So now, going that way, what should I put here? I should put the coordinate, because from here I went from X, I went to D, and Y end up to E. Look, and I go like this one more time. X become D, Y become E. Everybody understand what I'm saying? That here, X become D. I have to put anything I see at D here, and I put here E. So at D, I put 8. I put 8 there, because they're normal. And the shear stress is plus. So therefore, or going clockwise, so therefore I put clockwise there. On the other side, I put 8 and 8. And the other side going counterclockwise according to that rule that I showed you a minute ago. So you have to have that arrow there, this arrow and that arrow. Without those arrows, you cannot so do that. So this is head to head, toe to toe. You end up with this one. This is showing the stresses at D and E. This one shows the stresses at A and B. These are the plot. Is not going to be asked. Is that understood? Yes? A little bit rush, I know that, but they are so sort of quiet. I can see that, yes or no. But this is the idea of the Mohr Circle. You need to explore this much more. This is just the surface of it. Everybody understand that? You are going to see more of it in ME 219. I'm civil engineer, are going to see a lot more of that in other classes. Is that understood? So it's not there. There is a lot more into the Mohr Circle. I don't have time. I'm just rushing it a little bit because I only had 45 minutes for this. It takes 2 hours to explain it properly. Is that understood? Yes? So I'm just limiting your question to the equation I gave you. Is that understood? Yes? However, the state of stress is something you have to work on it from chapter 1 to chapter 6. No question.
The shear is 5, right?
No, the shear we end up was 8 and 5. The magnitude of, what did I put there? Oh, I didn't put that. The magnitude was 5. I'm putting the coordinate of here, 8 and 5, 8 and minus 5. That's what I did, according to that arrow. I just follow the arrow. Is that understood? Yes? Okay. Now, notice that if this item, if this item is part of a structure like that, this is what we are saying that, guys, at the end. So you calculate your X and Why? You be interested to find the stresses along 22.5 degree, but the principal stresses are somewhere else. Is that correct? Either could be here or there. Everybody else, or maximum shear could be somewhere else, and this is the relationship. Is that correct? As you see here, this plus that, this is another thing you want to pay attention. 2 theta p plus theta s is equal to 90 degree. Theta p plus theta x is 45. Look at it. This is going down 24.6 without you realizing. This goes up 18.4. So the sum is 4. This is always happen. Now, I asked this question from the other class. If I give you a stress like that, and I put, let's say here, 14 KSI, and I put here 4 KSI compression. What's the principal stresses here? You don't answer. You probably know that question. What's the principal stresses here? I just want to see whether you see all of this or not. Is there a shear there? No. If there is no shear there, aren't you already here? Already that is a, remember that, write it down. That's the whole clue here. If there is no shear, you are already having a principal stress scenario, yes or no? Because there is only 2 points on that circle, guys. There is only 2 points, or this diameter, or this 2 points. Every other point, look at it. There is a tau there. Is that correct? Except principal stress. This is a principal stress, yes, because there is no shear. Look. Is that correct? It looks similar to that. However, it happened to be in the direction of x and y. As a matter of fact, can you plot a Mohr circle for that? This is A, this is B already, guys. See, this is as simple as that. Therefore, if this is sigma, this is tau. We should always remember that arrow just for the sake. There is no shear here, so I remember. So I go here plus 14, and I go here minus 4. Yes or no? Correct? And these are my 2 principal stresses. This is my circle. Is that correct or not? So what's the diameter of the circle? That's 14 and 4. So the radius of the circle, that is 18. So that's 7. Everybody see what I'm talking about? Yeah. So 18 divided by 9. Yes. 9. And therefore, here from here, the average is at 5. Is that correct? Average 4? Yeah, 5. 14 minus 4, average becomes 10 divided by 2, 5. Is that understood? Because what I've given you here, no shear, no shear, no shear. This is the key for all the future problems. When there is no shear stress, it is already a principal, because there is only one on the whole circle. There is only one line with no shear. Look at this x. It has this much tau. This x and y has this much tau. That x and y has that much tau. Everybody see it. Okay. Now, what else? How much time do I have? 10 minutes? 10 minutes? Okay. So let's do one more problem. Not of this sort. This is the end of that. Any question there? Do you want to ask any question? Because I want to do one more state of stress. Notice what you have 2, 3 questions here you are going to involve there. That we have worked 9 weeks on it or 10 weeks on it. I show you how to find the state of stress. Chapter 7 is all about something for future. Any design that you do in future has to go first through the principal stress, because principal stresses are the one that causes the crack. Is that correct or not? Not the one that you are calculating. That's always x and y. So this becomes very important issue, and there is a lot more to it than that one. Now I want you to show you, at least technically, I want to show you, there are a couple of problems I have given you, that there is a circular. Remember the one I did last week was a plate with the vertical, with the rectangular cross section. This is the next one you want to pay attention, guys. Since I don't have time, I'm going to do it this way, so probably I'll do an example like that. Here is a cross section of the rod. Let's say that we are going to go problem number, I don't know, there is a handout problem there. Let's say that I give you a rod like this, and I put here a load like that, 2 kilonewton, right? It's something like that in your handout. And let's say this is equal to 1.5 meters, and this length is equal to 2.5 meters. And somebody comes and asks you that, this is at the middle, of course, 2 kilonewton hanging there. There could be more forces there. So one force or two force or three force does not make any difference. It just makes the problem a little bit more complex. Yes or no? Let's say that you adhere near the wall. Here is the fixed support to the wall. And there is some point, one point on the top, let's say go edge, and the other one on the side, okay, like here. Usually this is the type of question it is in your file. You see there is a point there and there is a point here, yes or no? And you want to find the stresses at that point. Notice there is no chapter for this. We already practiced that and we should already know that. So all I'm going to tell you is the following. Forget about that problem. Listen to me carefully here. Now, if I give you 2 points like that, yes, all depend what kind of internal forces you have. This is very simple. Everybody have done in the past, but this is putting it all together. Okay? This is the cross section. This is not here. This load, when it goes to here, it becomes a torque, it becomes a bending, it becomes a shear force, it may become a normal force, depends what we have. Is that correct or not? But we may have all of that here, yes or no? If I have a force going this way or this way, let's say going this way, what action do you have here and here? What chapter is this one? This is axial load, yes or no? This has nothing to do with this load. This is axial load. There is a sigma here either going in or coming out in that direction, yes or no? So if this is happened to be x direction, sigma is in the x direction. If it is in the y direction, sigma is, everybody see that, the sigma, you have done all this problem, but students have usually trouble putting everything together. So I am holding like that, I'm pushing it down, there are sigma going here all the way. So, but you see the same thing here. Sigma going in, sigma, that is chapter 1, yes? Then what did we do in chapter 3? Now I'm reviewing the whole chapter book for you guys in a way, in 10 minutes. Okay, what did we chapter 3? The chapter 3, there was a torsion there, yes, torque there, yes? There could be here, look at it. If I put this load here, this rod is going to turn this way, yes or no? That, for that rod, that is a torque, is that correct? So the torque either going clockwise, or clockwise or counterclockwise. If it's going this way, the action will be, look at it, the action will be, if you are looking at this point, the action going like this. So that's your tau xy, you see that? So it doesn't matter. You look at the point, you draw your tau this way or that way. That's a TC over J. You have 2 points here. Again, torque. Here, going this way, here going that. Yes? Going that way, you put it upward. So depend how you look at it, you put it there. Yes? Now, what did we do after that? Forget about shear and moment diagram. Go to the principle. Was the bending? Yes? Now again, the bending is the same thing. Everybody understand that. If you do bend here, this is the whole idea. I put 2 points here similar to that. So once you cut it, once at the end you bend it. Is that correct? If I put this load here, it's going to bend. So this point on the top, it's under tension. On the bottom will be under compression. In this one, nothing. Is that correct? However, if I bend it like that, then what? Then this one under tension, this one under, nothing there. Everybody, so the same thing happening here. In this cross section, I may have a moment like that. If I have a moment like that, this is the compression, this is tension, nothing here. If I have a moment like that, this is compression, this is tension. Everybody understand? That's the bend. Then the last chapter, which was chapter 6, was the shear force. If I have a shear force like that, here is 0, here is 0, here is maximum VQ over IT, you need the Q of that. Is that correct? So this is what we call it a state of stress, which comes from this kind of problem. I don't have time to do it. All I want to show you the static of this one. Is that correct? For you not to make mistake, this is in your handout, similar, exactly like that with different number. Now, you have to do 2 things here, guys. So to get to that point, and from that point go to the Mohr Circle, this is the entire book in one problem. First, you have to come up with the state of stress in top or on the side, yes or no. Then you have to put it through the Mohr Circle. All of that could be one question. However, cover the entire book. Of course, I'm not going to do that way. I'm going to give you different homework, including one from chapter 7. Everybody understand that? Now, you cut it here, yes? So this is the back. That's the front again, very near the wall. Is that correct or not? You have 2 options here. Anything that is happening here. When it goes there, it becomes equal, and this side and this side, or in this rod, should be in equilibrium. Everything you put on the other side should be equal, and so in other words, this becomes equal and opposite to that. Then on the other side become again equal and opposite. I always show this one, which is equivalent. Is that correct? I have talked about that before. So here is your point. Here is your point, reference to just what I told you there. Is that correct or not? Do we have an axial force here for this problem? This is a static. If you have a problem with the static, don't start this problem at all. Is there an axial load there? No, because if I want the axial load, I should have put a load here. Everybody that will be transferred into axial load. Everybody knows that. Is that correct or not? So there is no P over A here create stresses going. Is that understood? Okay. Is there a shear force there?
Yes.
Yes. The shear force is chapter 6. Look at it. Is that the shear force there? Equal to how much? 2 kilonewton. Right? So this is now a stress due to chapter 6. This is a force, but causes a stress, which was chapter 6. What stress do I have here? 0. What stress do I have here? 0. What stress do I have here? Which direction, first of all, does it go? It's going downward. I don't have time to do it. You have to present it like that. Yes, that point becomes like this. Yes, and the stress is going down. So I'm showing this stress. The stress is like that. Is that correct or not? Yep. If I'm showing the top one, I'm showing it this way, but then I can turn it around. Nothing there because 0. Is that correct or not? So this will be, I don't know what color, I call it this one K, this one H. So let's say this is the H and this is the K. So there is nothing else there. So this one goes there. Now, what else do I have here? Do I have a torsion here? Yes, so everybody knows that this one creates a torsion here. Is that correct? Which is 2 kilonewton times 1.5. Which way does it go now? Again, look at it. This is counterclockwise. This is clockwise. Here is, so you don't have to write. So go here and this action. That's the action side, the equivalent side. Is that correct or not? Yes? So it means here I have a torque going like that. So it creates a shear stress here and shear stress there. Yes or no? So look, and here this tau already become VQ over IT and TC over J. But since this is going this way, this side going that way, I'm showing it that way. This is first we decide that one. This should be equal and opposite. Then toe to toe, head to head. Is it plus or minus? This is original one. Has nothing to do with the Mohr circle. Is it plus or minus? Minus. So this is minus. This is minus because both of them going down. Everybody see what happened there? Yes? Correct? All right. How about the top one? The top one, this tau, this is for K. This tau, no effect of this one because this one doesn't have an effect there. Is that correct? But the effect of this one is going that way, which is this way, that way. So that way and that way still is minus TC over J. This one doesn't have effect, that one is. Is that correct? Or now, the people, when I give this problem, they end up with this, which is they usually forget about the bending. There is a bending there. Everybody see that? Everybody see that? If you are not, pay attention to that. All I'm saying that. What happened here, if I were you, if you're making a mistake, this load first comes here, become a force and a torque. But when it is hanging at that end, it's going to bend in like that. So on the top, you get tension. On the middle, you get nothing. On the bottom, you get compression. So on the top, you get a tension like that. So that is the one which you get sigma equal to MC over I. That's it. That's all your stresses there. Is that correct? Those are the state of stress for point H and point K. Did you see what happened there? You just look at the cross section. You just draw your stresses perpendicular to the cross section or parallel to the edge of the point. Is that correct or not? Yes? Very simply. So